Welcome back. In the last session, we had seen the problem number 5, and I already gave the procedure and then almost done. You need to substitute and then tell me ID1. After substitution, what did you get? Did you get ID1? Let's substitute. Therefore, ID2 by ID1 is equal to VD2, 2 minus 0.8 divided by VD1, 1.6 minus 0.8 whole square. What is 2 minus 0.8? 1.2. 1.6 minus 0.8? 0.8 whole square. What is this value? 0.3 divided by 0.2, right? Whole square. 3 by 2, which is 9 by 4. Then what is our ID2? Therefore, ID2 divided by ID1. Then what is ID2? ID2 is equal to 9 by 4 into ID1, 0.5, which is nothing but what? 1 by 2 milliampere. Therefore, which is 9 by 8 milliampere. Definitely greater than 1 but close to 1. What is the answer? No need to solve. Greater than 1 but close to 1. Only we have one answer, 1.125. Therefore, 1.125 milliampere. This is what is our ID2. I hope everybody understood. Okay? Take it. I will give you 1 minute time. Just try to do it. The people who already solved, good. Then try to match or try to see whether you got the same answer or not. But if I do any silly mistake, please ignore. Don't take it as granted. Okay? If you are confident that whatever procedure you have done and that is what is correct, and then if you prove that I did some silly mistake, not conceptual mistake, some silly mistake, that you can correct and then you can take it on your own. Okay? That's fine. Procedure is important, and if you solve the problems with the procedure without any silly mistakes, you'll get definitely accurate answer. Even though you know the procedure, even though you know the concept, if you do some silly mistake, right, you will not get correct answer. Write down problem number 6. After this we can start chapter 4, op-amp. That will take more number of sessions because it has so many applications. Amplifiers, integrators, differentiators, filters, square wave generator, triangular wave generator, sinusoidal oscillations, regulators, right? All will come under op-amp only. There are many applications of op-amp. but that will take huge time. I think out of so many chapters, I think chapter 2 BJT amplifiers took so much of time, and chapter 4 also will take so much of time. Okay, that's fine. Now write down problem number 6. The problem is the measured transconductance GM of NMOS transistor operating in linear region is plotted against the gate voltage at a constant drain voltage VD. Which of the following figures represents the expected dependence of GM on VG? Okay, therefore the plots are given. Okay, that's it. This is kind of theoretical problem, but we need to take the equations to prove or to get the graph. Okay. Let me give you the options, because options like now if you see the problem number 6. Now option A, this is what is given. This is VG and GM. It is like, and then option B, this is VG and GM. Option C, this is VG, GM. Option D, VG and GM. Therefore, which one is true? This is the problem. Okay. Which is true? Asking what is GM with respect to VGS. Remember, whatever GM plots I gave, like voltage bias, current bias, technology bias, they are valid only when the transistor is in saturation. But here he is saying transistor is in linear region. Therefore, don't say that answer C is correct. Okay, because that is true with respect to voltage bias, that too when the transistor is in saturation. But here he is saying specifically transistor is in linear region. When transistor is in linear region, then all these whatever plots we had seen, they are not valid, because we did only for saturation region. Okay. Now we need to derive once again. Before that, sometimes when you solve the problem using the correct procedure and the formula, and you got some answer, if that answer is not there in the options, what will you do? And you are very much confident that your answer is correct. Then there are two ways or two possibilities. Number one, either answer is not there in the options, then you will get free marks. Number two, whatever answer you got, yes, that is true, you need to get approximate answer to the existing plots or existing options. Therefore, only there are two possibilities. Either answer is not there in the options, then you will get free marks. Number two, whatever answer you got and then you are confident that your answer is correct, then possibility is you have to get the answer nearer to your exact answer by looking into different ways. Okay, let's see. First of all, let's derive. When the transistor is in linear region, when MOSFET is in linear region, tell me what is ID? ID linear, right? ID linear region, I gave you, right, is equal to mu n Cox W by L into VGS minus VT into VDS, right? Then this is what your ID. Then what is your GM definition? Definition of GM is equal to change in ID due to change in VGS when VDS is constant. GM is nothing but change in ID due to change in VGS when VDS is constant. Therefore, differentiate, then what you get when you differentiate with respect to VGS, you will get mu n Cox W by L into differentiation of VGS 1, 0, differentiation of this is constant, right, into VDS. This is what is your GM, right? Therefore, tell me what is GM now? You are trying to plot. Therefore, when you try to plot with respect to what? Not with respect to VDS, now with respect to VG or VGS, right? What is GM? Tell me what is GM? It is independent of VGS, right? It is independent of VGS. Therefore, even though VGS is changing or VG is changing or GM is not changing, means it is constant. And then value is mu n CS W by L into VDS. For what VDS you are saying are constant, that is what your GM. GM is function of VDS, not VGS. Right? But you don't have any option. I told you, right? And I am very confident that that is correct. Let us say. Or you did some silly mistake. But I am sure that I did correct. Then there are no options. Then what to do? We don't have options, right? A, B, C, D. I didn't see. Then I told, second possibility, try to adjust it to get to the nearer answer. Nearer answer means maybe try to adjust, right? Now, if you see here, can I write this equation in terms of ID? Therefore, what is mu n Cox W by L into VGS? ID divided by VGS minus VT. Let us say this is what your star, right? Therefore, this is nothing but mu n Cox W by L into VDS is nothing but ID by VGS minus VT. Can I write it like this? This is form number 1, this is form number 2. With respect to this is also your GM. Right? Now, if you ask me what is the plot, now I am taking with respect to VG. Assuming ID is constant, I am assuming. But nobody told me. Nobody told me to assume. But he is saying to get the answer which is what is available. I am trying, I am assuming. Right? Therefore, I can assume because nothing is told that your ID is fixed or ID is not fixed. Therefore, if I say ID is constant because that is related to voltage bias, this is what is related to current bias. We have two possibilities from practical analysis. Therefore, based on that I am saying, therefore ID is constant. Let us say current bias. Let's go to current bias. Then, this is constant. Y axis, X axis. XY is equal to constant. Rectangular hyperbola. Therefore, now what is your GM with respect to VG? When ID is constant, therefore, this is what is voltage bias. With passive load, voltage bias means your RD is present, and this is what is current bias. This is with I bias at the output, active load. With respect to current bias, what are we getting? Answer D. I hope this is clear. Take it. See, every problem is explaining something, right? Am I correct or not? Every problem is giving you one point. Therefore, if you solve multiple problems, then almost the theory will be covered. See, all these things are known to you. Don't you know the current equation? Don't you know the definition of GM? Don't you know the differentiation? But now, you know everything like what is what. But when you solve the problem, you'll understand how to collect them and then to use and then to solve the problem. That is what is very important. That's why problem solving is must. Even though you don't know the theory, fine. But if you solve the problems, you may get the theory. You may understand the theory also. Okay? But there is a special case, if you understand the theory perfectly, then you can solve any problem. But the probability of knowing everything is very difficult. Nobody knows all the things 100%. If this is over, problem number 7. Done, right? Now problem number 7. In the following circuit, employing pass transistor logic, I'll explain what is pass transistor logic. All NMOS transistors are identical with threshold voltage of 1 volt. Ignoring the body effect, the output voltages at PQR. Okay. Option A, option B, option C, option D, different voltages are given. Okay, doesn't matter. Problem number 7. Three transistors are in series. Five volt. All are having 5 volt. Like 3 switches in series. And now, what is the input? Input is given as 5 volt. This is what is the input. This is input, and this is control voltage, and this is P, this is Q, and this is R. Asking for PQR. Okay. Now, all are NMOSes and all are having threshold voltage. All are having threshold voltage 1 volt. Okay. There is no body effect. This threshold voltage is independent of the bulk voltage. Sorry, source to bulk voltage. Before directly solving the problem, let me explain. Just listen. This is what people call as pass transistor. Actually, we had seen this in a different way. If you take CMOS inverter, right? This is PMOS and this is NMOS, right? And I told this is your output, right? V0, and this is your VDD, and this is the input. If you observe clearly, remember, I can say that this is a pass transistor. It is trying to pass, but the gate voltage whatever we are applying, that is not the input voltage. Now it is trying to pass the input. This is 0. Input is 0. It is trying to pass 0 to output. This is also pass transistor, but the gate is controlled by input. Therefore, this is input. Now it is trying to pass the voltage from source to drain. Both are trying to pass the voltage from source to drain, or this is also trying to pass from source to drain. Both are pass transistors. That time I told both are fighting, then the voltage is in between. That's why I told, right? Therefore, this is source this is drain, this is gate, right? Therefore, input is the one which is what is controlled. Let us say when input is 0, then gate is 0, it is off. Therefore, it is not trying to pass this voltage from here to here because it is off. Now, when input the gate is 0, then VGS is there. Therefore, this is on. Then it is trying to pass. It is passing VDD. Therefore, because the input voltage is the one which is what is controlling, right, both NMOS and PMOS. Therefore, passing either 0 or passing either VDD. That is what is happening. That is what is nothing but a CMOS inverter. But for a given voltage, one of the transistors will be conducting, one of the transistors will be cut off, right? Therefore, if one of the transistors is conducting, right, then that will come or this will come. Simple. Whatever it is conducting, you will get it. Okay. Similarly, is speaking about only, I am taking just NMOS. If you take NMOS, then input is given. All gates are given 5, 5, 5. Then whatever voltage you give, let us say you are giving 0 volt here, the 0 is coming here. Maybe if you give 1 volt here, it is trying to get here. If you give 2 volt here, trying to get 3 volt here, something like that. That is what we are trying to see. But here, it is given like 5 volt. But we should know what is higher voltage, what is lower voltage. Okay. Now the same thing let me take just to explain. The same transistor I am just taking like this. Okay. Now I don't know this is what is. Now I am giving, let us say Vi is equal to 5 volt. According to you, if you think from CMOS inverter perspective, when input is equal to 5 volt and this is 0, your VGS is maximum, right? Then it is on. What is VGS? Let us say this is 5 volt. Then 5 volt, 5 volt. VGS is 0. This is off. Then this 0 will come here, right? Therefore, the 0 is going here. Therefore, it is what is pulling down. 0 is going here means it is what is pulling down. Your output is going to what? 0. Even though the capacitor, whatever you have here, this is nothing but your load capacitor. Even though this is what is charged, this will be discharged. Therefore, this 0 is going here. Therefore, your output voltage is going to 0 volt under steady state, right? Because your capacitor is discharging, because this is going. The same thing I am explaining. Therefore, now what is gate voltage? Let us say gate voltage is equal to 5 volt. Okay. Now this is what is my capacitor. Let us say this is CL, the load CL. Then this is what is CL. Okay. Now I am giving input voltage. Let us say this is what is my input voltage. Input voltage is 0. See, the same scenario I am explaining and just mimicking to a past transistor case. Okay. And this is what is my output. Let us say this is what is my output. Okay. Now you imagine, I didn't say which is source, which is drain. But here clearly you know what is source, what is drain, because source is always lower potential. Source is always lower potential. Now tell me, let us say it is definitely this voltage, let us say this voltage is greater than or equal to 0, then definitely this is lower voltage, no doubt about it. The terminal which is what is having lower voltage, that is source. For example, if this is 5, it is 5, then this will be source. Why? The terminal will be always having lower potential, that is what is source. Okay. But here this is 0, this is lower voltage, lowest voltage. Therefore, you can treat this as a source. Therefore, now this is source, this is drain, this is gate. Now tell me what is VGS? VGS is 5 volt. That is fine. Now we are trying to pass this 0 from here to here. Therefore, that's why this is what is called pass transistor. It is passing from here to here. Fine. Therefore, ultimately tell me, therefore what is your V0? Ultimately, your V0 is equal to 0 under steady state. Therefore, you will get 0 volt from here to here. You will get 0 volt from here to here. If even it has some voltage, that will be discharged through the transistor to ground, but whatever may be the 0 is coming to output. That is what is your pass transistor. That is fine. Now, let me ask you another question. This is important. If you understand that question what I am asking now, this is straightforward. This is nothing. Okay. Now, tell me. This is what is number 1. Now, number 2. Let us say this is what your pass transistor. Now, right? Now, I am not giving 0. Let us say Vi is equal to 5 volt. I am giving 5 volt. Okay. Now, I cannot say this is source because source and drains are interchangeable. That's why the arrows are not represented anywhere. Okay, that's fine. And let us say this is what your capacitor. But I am giving 5 volt here. Now I am asking what is your V0 under steady state, right? Therefore, now tell me, your V0 can be higher voltage or lower voltage. We don't know anything, right? You can start with what? You can start with some voltage, let us say 0. because always we can start with 0. If output is 0, let us say your output is 0 at a time t is equal to 0. We don't know what is the voltage, therefore let us start with 0, right? Then tell me which is source, which is drain. Now don't say this is source. The terminal which is what is having lower potential, that is what is source. I already told this point, but again proving with the example. Therefore now this is source, not this. The terminal which is having lower potential, that is what is source. Now tell me what is gate to source voltage. Now this is gate, now this is source, this is drain, because this is the input now. Therefore when I say this is source, gate to source voltage, right? Therefore now tell me source is 0, then what is VGS? Therefore VGS is equal to 5 minus 0, 5 volt at a time t is equal to 0. Then can I say our MOSFET is conducting? Yes, because channel is formed, because VGS is greater than or equal to VT. Let us say VT is equal to 1 volt. Then it is channel is on, then this 5 volt is trying to pass from here to here. Now tell me when 5 volt is trying to pass, then this 5 volt is trying to go, therefore your capacitor is charging. When this capacitor is charging, then the voltage is increasing. As the voltage is increasing, if you observe clearly, as the voltage is increasing, the source voltage is increasing, then your gate voltage is 5 volt. As source voltage is increasing, then VGS is decreasing. As VGS is decreasing, the minimum gate to source voltage required to form the channel, therefore you see the current through the channel is nothing but threshold voltage. Let us say threshold voltage is 1. Therefore when this VGS is less than 1 volt, your transistor will be off. Therefore the minimum voltage, therefore the maximum source voltage can go up to 4 volt only, not more than that. Why? Let us say this is what is going to 4 volt. Therefore it is trying to charge, therefore charging, therefore trying to reach to 5, but the moment it crosses 4 volt, then tell me what is your VGS. This is what is under steady state. At a time t is equal to infinity means not like 100 years. Infinity means under steady state. That is what is the meaning of time t is equal to infinity. Okay. Now tell me what is your VGS at time t is equal to this. Therefore now whatever VGS you have, 5 volt minus 4 volt, this is 1 volt. If this is trying to cross more than or equal to 4 volt, then it will be less than or equal to 1 volt, then it is off. Therefore at a time t is equal to infinity. Therefore tell me what is your ultimate output voltage you have. Ultimate output voltage you have is nothing but the input voltage whatever you have, right, is minus VT of this highest voltage, 5 minus, because both are same voltage, highest voltage of this you will get here, minus VT, 5 minus VT. Therefore that is what your 4 volt. That's why you know what people say. When you say this is logic 1, when you say this is logic 1 here, this is logic 1 and this is also logic 1, right? Okay, this is logic 1 only, that is fine. But what I want to say, your NMOS, if input is logic 1, it is not able to pass as it is. 5 became 4 only. But if you see logic 0, if input is logic 0, it passes as it is. Therefore we are getting what? This is what is called strong 0. Strong 0 means 0 volt you will get as 0 only. But here 5 volt you are not getting as 5 volt, you are getting as 4 volt. But still you can, in digital people treat it as logic 1 only. But this is what people call it as, this is nothing but weak 1. Your NMOS passes logic 1 in a weak way. That's why we don't use NMOS to pass 1. We use NMOS to pass 0 to output. And we use PMOS to pass 1. Because PMOS passes logic 1 strongly, PMOS passes logic 0 weakly, whatever in a weak manner. And whatever you have done, if you do the same thing for PMOS, you will understand PMOS will pass 5 volt as it is, but PMOS cannot pass 0 as it is. It is having some weak, it will have some 1 volt, it will stuck at 1 volt and then it cannot pass 0. That's why that is what it is. You take this, then we can solve the problem. This is also straightforward. You take this first. Okay. And before that, maybe before solving this problem, this is case 2, right? Now let me give you case 3. I don't have space, that's why I'm writing here. Then we will respond to the once 1, 2, 3 covered means problem is over. Okay, let's see. Now what I'm doing, we don't know what is source, what is drain, depends on the potentials. Let us say my input voltage is 4 volt. Now this is gate, okay, this is 5 volt. Now I am asking what is output. You are taking capacitor. Nobody is asking you to take, but that will help you to get the answer, right? Then what is your V naught? Can anyone tell? This is higher voltage, right? Now let us say the voltage what you have, let us start with 0. Therefore, this is what? Always start with 0 if you want. 0. For NMOS always start with 0. For NMOS always start with 0. For PMOS always start with highest power supply. Then at the time t is equal to 0. Okay? Now tell me, what is source, what is drain? Lower potential is always source. 0 means source, drain. Now tell me, what will happen? VGS, what is VGS? 5 minus 0. Therefore, what is VGS? VGS is equal to, tell me what is VGS? VGS is equal to 5 minus 0, 5 volt. At the time t is equal to 0. Right? Now, as the capacitor is charging through what? Through input, then this voltage is increasing, then it can go to what? You may think that it will go to 1 VT drop, right? 4 minus 1, 3. No, it will go to 4. It will go to 4 volt as it is at the time t is equal to infinity. Why? Because the gate to source voltage, it can go to 4 because this is 5. Let us say gate voltage is 4, then it will go to 3 only, because we need minimum gate to source voltage, that is what is want to pass, right? It should be conducting, then only this will come here. Therefore, when this is 5 but input is 4, already we have, when it is 4 it can pass 4 because VGS will be 1 volt, therefore it is conducting. Therefore, in this case because what is your VGS? Your VGS is, then this is 4, 5 minus 4, 1 volt, right? At a time t is equal to infinity. Right? Therefore 4 volt will be passed as it is. Okay? If you combine case 2, case 3, you'll get the answer. Done. That is what you need to get it. First you take case 1, case 2, case 3. I think case 2, case 3, if you combine, you can solve the problem very easily. That is what is problem number 7. Okay? All are passed transistors, all are in series. But input to all gates are connected to 5 volt. That is the scenario we have taken, right? And input is not 0. Input is 5 volt. The external, the original input is 5 volt. Whether the 5 volt is propagated to all pass gates output P, Q, R, that is what is asking. What is that 5 volt? Over? Now, directly I can apply onto the problem itself. Now tell me, let us say all are 0 at time t is equal to 0. Let us say this is 0 volt, this is also 0 volt, this is also 0 volt at time t is equal to 0. Remember, for all NMOSes you can take 0 as initial voltage. for all PMOSs wherever you deal, initial voltage you can take it as higher voltage. Okay, so that's fine. Therefore, now tell me, this is source. Now tell me what is source, what is drain for this transistor, which is having lower potential. This is what is lower potential. Therefore, this is source, this is drain, this is gate. Okay. Now, tell me, you have the capacitor here, right? Everywhere you have capacitor. Then, everywhere if you have capacitor, assume that capacitor is there. Now, this is 5 and this is 0. This is 5. Then what will happen? This 5 is trying to pass here. Then this voltage is increasing. As this voltage is increasing, maximum voltage it can go to, because gate is 5, the maximum voltage what we can get is, because the minimum gate to source voltage is required, that is 1 volt. Therefore, maximum it can go to 4 only, not more than that. If it is trying to cross to 4, let us say this is what is trying to cross to 4, then the VGS will be less than 1, then it will be off. When this is off, channel is not there, then it will be stuck at 4 only. Therefore, now this is stuck at 4 only. Actually, this is what is case 2. Input is 5, gate is 5, under steady state it will go to 4 only. Okay. Now, coming back to transistor 2. Now this is 4, this is 0. Let us say which is source, this is drain. This is drain, this is source, and this is gate. Okay. Now drain is at 4, gate is at 5. What is the maximum voltage? Therefore, this 4 is trying to pass here. Therefore, this 0 will go to what? Maximum it can go to, because this is 5, maximum it can go to 4 only, because it has to have minimum 1 volt. Therefore, whatever 4 volt you have, that will be passed as it is. That is case 3. When gate is at 5, if it is 4, it can pass 4 as it is, because the gate to source voltage 1 volt is maintained. Now, coming back to this, again, this is drain, this is gate, this is source, this will be passed for same case 2. Therefore, this 0 volt can go to 4 volt under steady state. Okay. Therefore, now tell me, what is the answer? Your answer is, your P will be 4 volt, your Q will be 4 volt, your R will be 4 volt. But you will not get 5 volt. 5 volt will not be passed, because this is weak 1. Your NMOS passes logic 1 in a weak manner. Answer is 4, 4, 4. Answer C. Answer is C. We have 10 minutes time, then I think we can solve. And the last problem, problem number 8. This is over. I'll give you 30 seconds. Then problem number 8, the last problem under student workbook. Then we can go to next chapter, chapter number 4. Case 2, case 3. For the first transistor, case 2. For the remaining 2 transistors, case 3. That's why practically people use transmission gate. Transmission gate is nothing but combination of NMOS and then PMOS. Whenever input is 0, PMOS will take care to pass. Whenever input is 0, NMOS will take care to pass. Whenever input is 1, PMOS will take care to pass. Okay, like that. It is a switch. Now the last problem, problem number 8. Let me read out. The problem is, in the CMOS circuit shown, electron and hole mobilities are equal and M1, M2 are equally sized. Say in that symmetrical CMOS inverter, the device M1 is in linear region if both the thresholds are 1. Okay. Don't bother about options, but options are required now to solve the problem. Okay. Okay, fine. Problem number 8. Straight away I can explain. Therefore, now this is your PMOS, NMOS, this is V in, this is V out, this is 5 volt, right? then mod VTP is given 1 volt, then VTN 1 volt. For what input voltage? It will be in linear region. Which one? PMOS, right? Yes, PMOS will be in linear region because M1 is PMOS. Okay. Now tell me, when input is equal to 0, we know that, right? If you take the transfer characteristics, this is what your V in and this is what your V out, right? I already gave. This is what is our VDD, let us say 5 volt, and input is 0, then you will get VDD at the output, that is 5 volt. Threshold voltage is 1 volt, right? This is 1 volt, and now this is what is 4 volt. This is nothing but VDD minus mod VTP, and this is nothing but VTN. Okay. Now this is what is 0 volt. Now see, therefore this is what is the portion, right? This is in this portion only you have that change. And I already told you, right? In this portion your NMOS, because when input is 0, let us say input is 0, your NMOS is off. Your NMOS is off. What about your PMOS? Your PMOS is in linear region or on. On means linear region. Why linear region? I'll tell you. When input is 0, under steady state what is your output? Under steady state your output is 5. Right? Then tell me case 1, when input is equal to 0, right? Then for PMOS, what is VGS? Because this is source, this is gate, this is drain. Therefore what is your VGS? Let us take mod VGS. What is mod VGS? 0 minus 5, 5 volt. What is your mod VDS? Drain is 5, 0. Therefore what is this region? This is nothing but linear region. If you take NMOS is off. NMOS, because what is your VGS? Your VGS is equal to 0. Therefore this is what is off, cut off or off. On means linear region, saturation is saturation. Now case 2, as we increase V in until you cross 1 volt, same region, same thing is expected. Okay. Let us say you are crossing 1 volt. When V in you are crossing 1 volt, but about 1 volt. Okay. Now tell me, if you are crossing 1 volt above equal to 1 volt, then it will be close to 5 but less than 5. I am speaking about this portion. Okay, I am speaking about that portion. Then you tell me what will happen. Your NMOS starts conducting. When NMOS starts conducting, then you can say, let's see what is PMOS state and then NMOS state. PMOS and then NMOS. Right? What is PMOS? When V in is greater than or equal to 1 volt, what is your mod VGS? Your mod VGS will be 1, 5 less than or equal to 4 volt. Then what is your mod VDS? Your mod VDS will be what? Drain is approximately 5, then it will be greater than 0 but close to 0. Now what is the region of the transistor? Your VDS is close to 0 and then VGS is close to 4, still linear region only. If you calculate you will get it. Now NMOS, what is your mod VGS or directly VGS? What is your VGS for NMOS? Close to 1 but greater than or equal to 1. What is your VDS? Close to 5 but less than 5. Then this is nothing but saturation region. Therefore remember your NMOS will be, after crossing this 1 volt, your NMOS will be entering into saturation, but your PMOS still it will be in linear region only. At a particular point, this is what your switching point. Here NMOS will be in saturation, but your PMOS will move from linear region to saturation region, and in this region your NMOS will be into linear region and your PMOS will be in saturation region, and in this region which I gave already, your PMOS will be off and your NMOS will be in linear region. Therefore tell me what is the answer? Only nearer to 1 but less than switching point. Nearer to 1 and the less than switching point, you can say your PMOS will be in linear region. Less than almost switching point, your PMOS will be in linear region. Answer is less than switching point means, let us say switching point is 2.5, then less than 2.5 or less than something. The answer is A. Answer is A. The option A is satisfied. That's it. Option B is not satisfied. Option C is not satisfied. Option D for all 0 to 5. No, that is not correct. Therefore, option A in less than 1.875 volt. This is true. Your PMOS is in linear region. Okay. Take it. Take the characteristics. See, actually this is what I've taken. I've explained this, right? These two. Now maybe this also I explained. We solved one problem, right? When input is equal to 2.5, then output is also 2.5. 2.5, both are in saturation. And this also I already explained. That is nothing but extremity. When input is equal to 5 volt, NMOS is on, PMOS is off. This is what you have to do. Like when input is equal to less than 4 volt, then if you see, you'll get the answer. Okay. This is homework for you. Except this, I already explained all the things. Okay. You have 2 more minutes. Maybe you can pause the video if you want to get it. Then, but the options, out of 4 options, only option A is satisfying. Remaining 3 options are not satisfying. We want less than switching point and close to the input 0. That is what? That is what is PMOS. It will be in linear region. Off means cut off. Okay.